Okay, the last couple sections of this book, and we're going to skip the very last section, which is pair production. But the last concept in this chapter, not in the book, but in the chapter, is one more thing that really couldn't be understood without quantum mechanics, and that's what's called the Compton effect. But to understand the Compton effect, we need to understand X-rays first. And should talk about the production of X-rays, because that's really part of the whole history. And this, how the history goes together in the end of the 1800s to begin 1900s, is so interesting how it all fits together, because it was in 1895 that Röntgen discovered X-rays in 1895. Now, can you guess how he discovered X-rays? Actually, you might know the part of the story. Part of the story is that they were discovered by accident. But how were X-rays? They were discovered by accident, but it was recognizing what they were that was the amazing discovery. Because they were discovered by accident, a lot of things have happened by accident that people probably just haven't even noticed. But it's that accidental discovery, and then being able to explain the accident, explain what you're discovering, that's amazing. So he wasn't lucky so much as he really figured something out. But what I was getting at is what was Röntgen doing when he discovered X-rays? He was playing with cathode rays. So he was playing with a cathode ray tube. So this is the big thing in the late 1800s, is evacuated glass tubes and what you can do with light and electricity. And what it turns out, and so Röntgen, the way that the X-rays were accidentally discovered is that he had some photographic plates that he developed, and it turns out that they were in some kind of protective box. But it turns out that when he developed these photo plates of, I don't know what he was taking photos of, but when he developed these photo plates, he found that there was an image of two coins that were sitting on top of the box. And he somehow figured out that the reason why there was an image of the two coins was because his cathode ray tube experiment was producing X-rays, which were a higher energy ray, which created this image of the coins on top of the box, just like sending X-rays through your body and creating an image of your skeleton, which is inside of your body. Okay, anyway, I don't know if that made a little bit of sense. It became understood that the way you produce X-rays, or the way that you can produce light, it's a reverse photoelectric effect. What you do is you bombard a metal with high energy electrons. So if you bombard a metal with high energy electrons, that metal will emit light. So it's the opposite of photoelectric effect, where you bombard a metal with light to emit electrons. Now, so how does this work? And presumably X-rays were called X-rays because, sort of like the cathode rays, they weren't known we didn't know what they were to begin with. We eventually understood that they were electromagnetic waves, just light, that invisible light, high energy light that you couldn't see. That's what it is, right? It's an electromagnetic wave, just like red light, blue light, green light is an electromagnetic wave. It's just a higher energy electromagnetic wave that's not in the visible spectrum. That's what it is. But it was understood that we could produce these unknown rays by bombarding metals with high energy electrons. Now, what's the process through which these were produced? It turns out that if you take these high energy electrons and you bombard a surface with these high energy electrons, let's just give them an energy. I know normally we give them a velocity, but we give them an energy. And the energy, they might be 100 keV electrons. I don't know if that's meaningful to you or not, but that's reasonable electron energy to produce X-rays. And you bombard this surface with these, and then what happens is you get photons off, high energy photons. These are high energy photons. In other words, they're X-rays. And everything's relative, right? So when I say high energy, everything's relative, but these are particularly high energy. They're dangerous in the sense that, well, you know how X-rays are dangerous. Okay. So how could we explain the production of these X-rays? Well, what happens when the electrons get into the material they come to a stop, right? The electrons don't just travel through. Well, maybe you don't know that, but that is what happens, is that they come to a stop, and that energy has to go somewhere. And that energy goes both into the material and heating up the material, but also goes into emitting photons from the material. So what happens is the electrons hit the material, they slow down, they come to a stop, and we therefore get radiation, right? So we energize the material by having these electrons come to a stop in the material. We energize the material, and it gets energetic enough that it emits photons. So because of this idea that in order to create this X-ray radiation, that we have to stop high energy electrons, it's called stopping radiation, but breaking radiation, as in stopping. So X-rays were also known as breaking radiation, breaking as in stopping, because it was slowing down and stopping the electrons that energized the material enough to emit the high energy photons. In German, that's called Bremsstrahlung. Bremsstrahlung means breaking radiation. I say that only because that's brought up in the textbooks or in the history, that X-ray radiation was also called Bremsstrahlung. Discovery was actually given the Nobel Prize. Röntgen, I know you say his name a little differently than that. Can't quite remember how to say it. But anyway, won the Nobel Prize in 1901 for his discovery of and understanding of how to produce X-rays. So keep in mind what's going on here in the material is this sort of interaction between particles and photons, right? Between electrons and photons. And that's what the Compton effect is about. The Compton effect, or Compton scattering, because it's about looking at emission of photons at various angles. Compton scattering is about interactions between photons and electrons. We'll come back to that in a second, but it's a question of the results of energy of light being scattered off of particles didn't make sense. That's basically the bottom line, is that the energy of light being scattered off particles, being reflected or scattered is the right word, send light in and then see what comes out, didn't make a whole lot of sense. Once X-rays were discovered, it was easier to make measurements, and hence the connection between the two. And then once it was understood that you apply the photon properties to light, Compton was able to explain the concept of what's going on when you scatter light off of particles. That wasn't until 1922, so this is a later thing, and he actually won the Nobel Prize for his understanding of this in 1927, so it was a big deal. But this is sort of a later, what it really was it was icing on the cake of 1905, Einstein suggests quantization of energy, of electromagnetic energy, and it wasn't well accepted. Actually, quantum mechanics was not well accepted until the 20s or 30s. And it was things like Compton scattering that was the final chink in the wall, the final experiment that wasn't understood, that is now understood and cements the new wall that has quantum mechanics in it. I'm really, really trying to drag out that analogy. Come back to X-ray production real quick, just to make sure we understand what's going on. You would be doing this in an evacuated glass cylinder or something like that, so that we can actually send these high energy electrons to a target and they don't just interact with the atmosphere around them, so hence you need the vacuum. You have an electron gun where you have a filament, right? That's this part right here. You've got a filament that is being heated up and it boils off electrons. You put them through a potential difference that accelerates them so that those electrons come out with a certain velocity or a certain energy. And then those electrons hit a target, and when they hit the target, they slow down, and that energy is absorbed and then re-emitted as photons. Okay, that is how you create X-rays. Even in your dentist's office. In your dentist's office, when you're getting X-rays, which is the place that we probably most frequently get X-rays, if you go to the dentist, and hopefully you do every once in a while, that they have the device is something like this, right? It's a high energy electron gun that hits a target and creates these X-rays that come out, or these photons that come out. And if you make that a high enough energy electron, then it's going to be an X-ray photon. And again, the X-ray photon just means it's a higher energy photon. So it's easier, because it's higher energy, it can penetrate better, which is why we use them to make images of the body, because they go through the body. Unlike visible light, which mostly is absorbed somewhat, but is mostly bounced off the body, X-rays are higher energy, they go through the body. The higher the energy of the photon, the more destructive it is, the more it can pass through something and create damage while it goes, but also it can pass through something and perhaps do something useful, like create an X-ray. So microscopically, what's going on, right? What's going on in here is that the breaking radiation, the Bremsstrahlung, is that these electrons, let's make the electron E minus, it's coming in with a certain energy, E initial, into certain total energy, E initial, right? That's the 100 keV electrons, or whatever we want to call them. And they are being accelerated by the positive nuclei in the target, right? So there are positive nuclei in the target. And what happens when an electron gets near a positive nucleus, it gets attracted to it. And so we're sending in these, I'm trying to get the right color, sending these electrons, and this, I didn't mean for it to hit head on. Typically the electron will go by and it'll be attracted, so it'll go around and slow down. And while it's slowing down, we're giving energy to the atom, which will then, what color was our photons? Oh well, I'm changing colors here all over the place. And which will then, because we have given away some of that energy, right? Some of that energy, the electron is slowing down because it's being attracted by the nucleus. The atom is now getting more energetic, and it in turn will emit the radiation as a photon. Okay. Now, what is the energy given to these electrons by this electron gun? Don't forget, the energy is simply the energy, or at least the maximum energy given by the electron gun, is E times V, right? The charge of the electron, times V, the potential difference that we're accelerating them through. So that's the energy given to the photons. If all of that energy is turned into, electrons. Those are the electrons. If all of that energy, if the electron came completely to rest and all of that energy was emitted as photons, then the emitted photon would have energy HF. So basically we can say that E times V for the electron gun equals H times the maximum frequency of the photon that could be emitted. Right? So it's going to be less than the max because there's the same concept of a work function, right? There's a certain amount of energy that it's just going to take to make it emit a photon, I guess. Energy is going to go into the heating up the material as well as, which is another form of electromagnetic radiation. But in any case, if it all went into simply creating photons, then it would be HF. So this is HF max. It might go, some of that energy might be lost elsewhere, so it could be a frequency less than F max. But this is really the equation of photon production in the reverse photoelectric effect, or X-ray production. And so we can see, if we want to get a sense of frequencies, red light, which is around 700 nanometers, 667 nanometers, whatever, has a frequency of 4.5 times 10 to the 14th hertz. You can figure out these frequency wavelength relationships simply because we know C equals F lambda. Blue light is 6.6 times 10 to the 14th hertz. Then comes ultraviolet, and then the X-ray spectrum starts at about 3 times 10 to the 16th hertz. So it's almost 100 times larger frequency than blue light. It's almost 100 times as energetic because remember E equals HF photons times blue light, so 100 times as energetic. And UV is somewhere in between. So let's just think about, for the low energy X-rays, the smallest energy. That arrow means 3 times 10 to the 16th hertz and bigger. It actually goes, the X-ray spectrum is pretty large spectrum. It goes up to 10 to the 18th hertz. So it's got a much larger range than the visible spectrum. Visible spectrum is just a teeny tiny sliver out of the whole electromagnetic spectrum. So let's just figure out what is the voltage required to create the electron, to give the electrons enough energy to create X-rays. So what is the voltage required to give enough energy to the electrons to create X-rays? So that's simply or the minimum voltage required. So we're just going to use EV equals HF, right? That F max means that's the maximum frequency it'll produce. So it'll be a frequency less than this. But in any case, even though we're using the minimum frequency for X-rays, this will give us a target for, we know our voltage has to be greater than. So we'll just use this frequency for the X-rays, and we'll plug it in, and we'll solve for voltage. We'll plug it in, and we get that the voltage required is... Actually, to my surprise, it's only 124 volts. I was sort of making up these numbers as we went. Well, making them up. They're all numbers we can look up. But I think that doesn't seem like a terribly high voltage. And that means the energy of the electrons would be 124 EVs. But I think here's the thing, is that that's the bottom of the X-ray spectrum. And X-rays go up by a factor of 100. So the minimum voltage might be 124 volts, and that's not really it's going to be bigger than that because because all the energy doesn't go into producing photons. And then if we want X-rays of higher energy, right, on the higher energy end of the spectrum, it's 100 times that. So it would be 12,400, 12 kilovolts, right, 100 times that. So anyway, it doesn't matter. The equation's still correct. The numbers are still correct. It's just not obvious that those are high energy rays or high energy electrons, but they are. And actually, one of the really important things that comes out of this is the fact that that you can go ahead and you can measure the energy of the electrons, and you can measure the energy of the emitted X-ray photons, and you find that this relationship holds. That is yet another confirmation of Einstein's photon hypothesis.